Yeah?
So, the videos that you make, where do you upload them?
I post them on YouTube. So I'll send everyone the link once the website and homework gets set up. I'll send everyone the link.
What's the avatar?
Huh?
Nothing. What's the avatar?
What avatar?
The YouTube, your YouTube avatar.
It's a Matrix bunny.
Uh,
It's funny, you know, Matrix costume.
was
Okay. She's like, what? Yeah. It's there to confuse people. Okay. So we were doing integration by parts. And I kind of put up this example last time, which hopefully we appreciate, that doing that by integration by parts would be highly annoying. If you can't appreciate it, you should do it. Wasting time now is better than wasting time later on a test, so you should kind of have the intuition about the approach you want to take on a certain problem. And so you kind of have to sometimes stumble around in the dark until you find the best way to do something. So that's actually going to be annoying to do it directly. We actually did it with x squared e to the x. You realize we had to do integration by parts twice. You have to expand all parentheses. And yeah, it'll get annoying doing it 5 times. So what we're going to do here is we're going to replace int by parts with an algorithm. That's going to be more efficient. And you can pretty much use this anytime integration by parts will work. This algorithm will work. It's just an algorithm to actually repeatedly churn out an integration by parts formula, and it's called tabular integration. So right now I'm going to describe to you something that's called tabular integration. It's kind of like a different technique, but not really a different technique. It's just a way to do integration by parts a little bit more efficiently. So here is how you would set such a thing up. So it's called tabular integration because you actually use a table. So suppose you have an integral and it's a product of 2 functions. I'm going to call it big F times big G. Okay. And suppose you want to actually approach this via the integration by parts way, right? So what I'm going to do is I'm going to think of as the big F as the guy that I'm going to choose to be the U, and the G to be the guy I would choose to be the dV, and so I lined it up like that. What you're going to do is you're going to construct a table right below that. This table is going to have several steps, right? Dot, 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 dot. Okay. And so here's how you're going to fill out the table. For the U guy, you're going to keep differentiating it, right? Because you start with the U and you find du and blah, blah, blah. You're going to keep doing that, right? So I'm going to find F prime, I'm going to find F double prime, I'm going to find F triple prime, and I'm going to keep going, right? And for the dV, I'm going to keep integrating it. There's not a very nice notation for that. I'm going to use subscript. Let's say subscript 1, that's the first integral. Subscript 2, that's the second. Subscript 3, that's the third. Okay. Now you're going to keep going until you end up with n derivatives. Now I'm going to tell you what n has to be. When do you actually stop the table? How long do you have to go for? I'm going to show you. And here, this is the nth integral. Okay. So that's the first thing. You're going to construct this table, right? You line it up so that your u and your dv are beside each other. Keep differentiating the du, and keep integrating the dv until you get to a certain opportune moment, which we're going to talk about. Now, once you have this table actually filled out, where I'm going to tell you when to stop, you are going to start to do multiplications along the diagonal. So you're going to take this f, you're going to multiply by that g. You're going to take this guy, you're going to multiply by here, take this, multiply there, take that, multiply there, and it's going to keep going. So right here, you're going to have like an f to the n minus first derivative, that's going to multiply this g. Okay. Now at the end, you're also going to do a multiplication, but you're going to multiply back that. Right? And this arrow is a different color because you're going to do something different. Now, what do you do on these diagonals? It turns out for the first diagonal, you are going to apply a positive sign to that diagonal. Now you might remember that the integration by parts formula has a negative sign in it, but once you start getting those nested parentheses, the negative is going to change all the signs. So if you have a negative and then you open parentheses, it's going to change the sign, and then if you open parentheses, then that it'll change the sign again. So you'll have a kind of alternating sign pattern going here. So you will actually apply a plus sign, then a minus sign, then a plus sign, then a minus sign, and you keep going. Now, by the time you get to the end of the table, you're not sure what it's going to be. It's going to be plus or minus. So because we don't really know how long this is going to be, it depends on whether we end on an odd step or an even step, and then you go across here. So now, here's how the answer is going to look like, and I'll tell you how to stop the table. Here's what your answer will look like. You're going to take all these products and apply these signs. So your integral of big F, big G dx, it's going to be big F times G1 minus. Now, one thing you can notice is that what this big F times G1 represents is the U times the V, right? Because your G1 is the V. So that's actually starting off the integration by parts formula. But then it's going to minus, and you're going to take this, the F prime times the G2, plus the F double prime times the G3, minus Stephen Colbert, right? And you're going to keep going, right? Now, ultimately, you're going to end up with this times that. That's going to be your n minus first derivative times your nth integral. And then in the final step, this going across here, what you're going to do is you're actually going to, well, it's going to be plus or minus here. It's going to be plus or minus based on what that was. Minus or plus. You're going to integrate the product going across. And that's how you end the process. Now you're going to look at all these products. You're going to integrate this integral at the end. That's going to be the last integral that you need for integration by parts. And that's actually what your answer is going to look like, believe it or not. Now, it might look a little bit confusing right now, but once we run through the process a couple of times, it should be clearer. Now, how do you know when to stop the table? How long do you continue this process? Well, stop when one of the following are achieved. One way you will know to stop the table is if the F eventually goes to 0, right? So, for example, if your F happens to be a polynomial, eventually if you keep differentiating it, you'll end up with a 0, right? Because you'll keep decreasing the power until you hit a constant, then you're going to differentiate that constant, it's going to hit 0, stop the table, once it hits 0, right? So that's one way you'll know how to stop the table. The second way to stop the table, this is if when you integrate across, when you look at the final row, you'll integrate, if you realize your F will never hit 0, what you keep doing is you keep checking the row. Now, one way you can know to stop is what this row would look like. If your f to the n g sub n dx is a constant times the original integral. Right? Including the fact that it might be exactly the same integral, right? So this is dealing with the case where we had something like the e to the x times the sine of x integral, right? Eventually you realize you run through integration by parts and you ended up with the same integral again. So that would be something like that would happen in situation 2. Now situation 3, and this is the last situation that you'd have to worry about. If your f to the n, if that last row is easy. Now easy is of course relative, but what I mean by easy is you realize that this integral that you see here, you can see straightforward how to do it by some other means. Like oh, that's just something I can use a substitution on, or oh, I can just use the power rule at this point, or right? You just notice that hey, this last row, if I just multiply straight across, the result is going to be something that I can deal with easily, relatively speaking. Okay. So that's the overall process. That's called tabular integration. Yeah.
When you say f eventually goes to 0, do you include the 0 or the one before the 0?
No, you include the 0.
Include the 0.
Yeah.
So the product will just be 0 then.
Yes.
Okay.
Which means you end on the integral of 0, and that means you get a plus c from that. Right? The integral of 0 is plus c.
Okay.
Let's actually do it. Let's actually do this one. So you can see what I'm talking about. What are you talking about, Jhevon? Okay. See what I'm talking about. So here's the x to the 5th, e to the x dx. So you see that, and of course, the first thing you're going to think about, do we have a basic rule that looks like this? No. Second thing, can I simplify it to use a basic rule? No. Substitution work? No. Okay. Now you get to the point where you say, probably integration by parts. Once you realize it's integration by parts, you're going to notice, heck, that's an x to the 5th. Me doing integration by parts, that's going to take 5 levels of integration by parts. That's pretty annoying. I wonder if there's a way to do this more efficiently. Then you think tabular integration, right? This all goes through your head in like 5 seconds, right? Like that's eventually, right? Probably not right away, but you want to practice to the point where it takes a few seconds for your mind to think through all these levels. Okay, so all right, now we're there. Okay, I know I'm going to approach this using integration by parts, and I know I'm going to use the tabular method. How does it look? So I'm going to, immediately below that, I'm going to start drawing and doing that. Okay, so what I'm going to do is I realize that the steps, oftentimes it'll depend on the f. Notice here, this is a polynomial. I know it'll eventually hit 0, so I'm just going to keep differentiating. 5x to the 4th, 20x cubed, 60x squared, 120x, 120, 0. Right? So your f, upon repeated differentiation, eventually goes to 0. And at this point, you stop. Right? Table is done. Now what you're going to do is you're going to fill in the other column, which you're going to do by repeatedly integrating. Now in this case, repeated integration is easy. It's just an e to the x. It's going to be e to the x, 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 e to the x. And now you're going to do the multiplication. You're going to multiply across here, across here, across here, across here, across here, across here, and back here. Okay? And what is that going to end up looking like? Well, it's going to end up looking like over here. So this is going to be equal to this times this with a plus sign. Right? So that's this one. Then this times this with a minus sign. This times this with a plus sign. This times this with a minus sign. This times this with a plus sign. this times this with a minus sign. And then you're going to have a plus the integral of 0. But of course, integral of 0, that's going to give you your plus c. And that's your answer. You can clean this up a little bit. E to the x is a common term. I guess I could factor that out. That's going to be x to the 5th minus 5x to the 4th plus 20x cubed minus 60x squared plus 120
You've got an
x minus 120 plus c. And that's the answer. And if that answer doesn't indicate to you that integration by parts would be very annoying, I don't know what will. But that's the answer. That's how you'd integrate that. Called the tabular method. Questions on the method? Yeah.
Do we ever on the exam need to factor all that out, or can we just leave that?
I mean, you could leave it like that if you wanted.
Oh, that would be
I think it's literally just for me to cut down on my writing. I factor it out to be lazy, actually. It's the only reason. It's not. Okay, so that's it. That deals with the first situation. You stop when you hit 0. Do that thing. You alternate the signs. And yeah, you add those all up. Do the final integral. In this case, when it's integral of 0, that's easy. That's just a constant. And yeah, move on. Let's do the one that actually revolved on itself. So, suppose I wanted to do tabular integration on this guy that we did last time. It's e to the x times the sine of x dx. Now technically following Leate, the t, the sine function would be the u, and that would be the e. Although, I did mention this last time. T and e are interchangeable. In Leate. There's-
Say what it means again one more time.
Oh, Leate is just a mnemonic. It stands for logs, inverse trig, algebraic, trig functions, and exponentials. It just tells you the order in which you choose to be the u. So this is a t, and that's an e. So according to Leate, I would choose this guy to be the u, so that's the guy I repeatedly differentiate, and this guy to be the dv guy I would choose to integrate. So let's not switch anything. So what I would do is I would switch these. So this is my u, and I am going to just keep differentiating that. So the derivative of sine of x is cosine of x. The derivative of cosine of x is minus sine of x. Now, I see that, you know what, this is just going to keep jumping back and forth. It will never hit 0. I'm not going to end up in this situation, so I'm not even going to try. At this point, I'm just going to keep doing one row at a time until something pops out. So e to the x, integrate that, you get e to the x, integrate that, you get e to the x. Now what you notice is that this row here, notice that that row is actually a constant times the original. Namely, minus 1 times the original. So at that point, we stop. Stop. I don't want anyone to think I can't spell stop. Stop. Do you know Jhevon spells stop like S-T-A? That's how rumors get started. Okay. Right? So once I realize that, hey, that's the same line that I started with, sure, it's off by a constant factor, but remember, constants, you can always factor them outside, right? So once I realize that the variable parts are the same parts that I started with, you stop the table, right? And then you're going to do that thing. You're going to multiply across here, then multiply across there. So this is going to be equal to plus e to the x times sine x minus e to the x times cosine x minus plus, and now I have e to the x times minus sine x, integral of that part. And now what you notice then is that the integral of e to the x sine x is equal to e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x, in which case you can take this guy and move it to the other side, and you'll get two of them, and then you divide by 2. Right, so we do that same thing at the end, but we know when to stop. And so we get the integral of e to the x sine x is 1/2 times e to the x sine x minus e to the x cosine x. That's a constant. So that's an example of when you'd stop in the second case. Right? Keep doing this table, you realize, oh, the u is never going to go to 0, so you just do one at a time, one row at a time, and realize, oh, hey, I got to a row that looks exactly like the original row, right? Might be off by a sign or a constant factor, but it's the same as the original. And you stop. You won't have the integral of 0 at the end, but you'll just have the integral of the original, which you just move to the other side and solve for, like algebra. Let's see working in the third situation. Again with a familiar example. I believe we did x squared ln x as well. So like that. Now this guy here is L, it's a logarithm. This guy here, it's A. It's an algebraic polynomial. Algebraic is the wrong phrasing there, but whatever. Right? So you know that this guy gets to be the u in integration by parts. Which means you probably want to start by writing it the other way. And then start doing that table. Now again, integration by parts on this one wasn't that bad. It worked after one step, but you can still actually do tabular integration here. So I would differentiate this. I would get 1 over x. That's never going to go to 0, so let's figure this out. I would integrate that. That's x cubed over 3. And I notice at this point, you know what, if I actually multiply across here, that's actually not so bad. That's actually an x squared if I multiply across. So at that point you stop. You just realize that you can multiply this, then multiply that. And so the integration by parts is going to give you plus x cubed over 3 times the ln minus the integral of 1 over x times x cubed over 3 dx. And at this point that's x cubed over 3 ln x. This will cancel that, x squared. So this gives you x cubed over 9 plus c. Same answer we got last time. Yeah.
So you could kind of look at the first exponent of x squared and try to see like for the other one x to the 5th, since it was a large exponent, you could say you knew that you could do multiple steps. But for this one, since it's 2, you can look in the earlier steps, right? Since the exponent is very small.
Yeah, but here the x squared wasn't the guy controlling it, the u is the guy controlling it.
Alright.
So here the ln x kind of determined what I was going to do. Like the x squared, this also goes to 0 upon repeated differentiation. It's just, it's not the guy I would be differentiating. Right? The ln is, right? So that's why I didn't really worry about the power of this actually. Once there's a log involved, that's the guy I'm differentiating.
Alright.
So at that point, I start differentiate, integrate. I try to keep the rows level because I'm not exactly sure in general when it's going to stop. And so I just stop whenever I get to a row where it's easy. Either it's the original of what I had, or just multiplying across is just a very simple thing to integrate. Right? Now, the first case of when you eventually hit 0, that's when the polynomial is actually the guy that's in the u position. Then you know, oh, I know exactly, I'll need exactly 7 steps here. Then it's easy. Otherwise, it's not really easy. Just do one at a time until you get something, oh, I know how to deal with that. Other questions? Let's do some more practice. We're gonna do these together as well. Where are we? More examples. We're going to do these together. So on your first test, pretty much the first problem is going to just be me asking you a bunch of integrals where you have to use different techniques to solve them. And I'm not going to tell you what technique you have to use to solve them, so I want you to recognize them. So you definitely want to be practicing a lot of drills. Every time you learn a new method, you practice a bunch of it. And then you mix up problems from different techniques and try to figure out which one to do. But we'll get to that one. But essentially, let's let's knock out some problems, try to get comfortable. Now, as I told you guys before that e to the x squared, impossible to integrate. Not that it's hard, it's just the answer doesn't exist. We kind of have to make up an answer, kind of like how we made up an answer for square root of -1 to invent the complex numbers. But surprisingly, e to the square root of x is actually very doable. Go. What do you do?
It's a times u prime.
E to the u times u prime.
So convert it into a fraction and make it a half a sum. And then
How do you do that?
like it's x to the 1 power.
Okay. How does that help?
I don't know, maybe it doesn't.
Yeah.
If you recognize that there's a 1 in front of the e to the
Okay.
then could you start the tape? Substitution or what?
Like, how would you even start that? Huh? What did you? Did someone say something?
Is
It says substitution by parts, but
Okay.
Yes, it's wrong.
How would you get that to work? just know substitution by parts? Do you really think I'd be that mean? First example, you have to do a substitution and by parts?
What's it use though?
You could choose a U and a DV.
Which would be?
Since using the Layate, the acronym, the U would be the 1,
Right?
and the DV would be the.
Which means
That doesn't work.
you'd literally get a 0 on the first step.
But wouldn't you have?
And then you'd have to integrate this, which we don't know how to integrate.
Yeah, it's just the
So,
same.
yeah.
So because.
So right, jumping into by parts directly isn't going to work. So yes, you have to do something first. And yes, the answer is a substitution. But what do you
Simplify.
substitute?
Simplify.
What would you
Is the answer
substitute?
e to the power square root of x over 2 to the square root of x? Or am I
No.
really wrong?
You are differentiating, not integrating. That's what the derivative is, not the integral. So what was when you want to do a substitution? What was the thing that you want to substitute? What made you do a substitution?
Function and its derivative.
Sure, but what was the first part? Like when you do substitution, there are two things you look for. One of it is if, okay, whatever I substitute, when I differentiate it, I should be able to swap that thing out, right?
Yeah.
But how do you make the choice in the first place?
One thing is related to the other thing.
So the goal of substitution is to essentially reverse the chain rule in the sense that you transform something that's complicated into something that's simpler, right? So if you had something like x squared times the cube root of x cubed minus 4 or whatever, right? Now, to do integration by substitution, what would you do? You would choose u equals this, right? Right? Now, why did you choose that? Well, yes, because I realize that if I take the derivative, then this part here is located there. But I hate to break it to you at this point, that nicety only really happens in Calc 1. Like, that doesn't even have to be a thing anymore, which it's not a thing here, by the way. So, yeah, Calc 1 is just very too easy. But more importantly, why did you choose that to be the guy to substitute in the first place? The reason was it made it simpler, right? You see, the x squared isn't the complicated part of this integral. The fact that I have a radical with a sum under it, that's the complicated part, right? The substitution was meant to take away a complication. Now, of course, in order for the substitute to work, in order for me to be able to swap things out, the derivative also had to behave, but that's an afterthought, right? The first thing is, that's complicated, I want to make it look easier. A sum under a radical is a problem because radicals don't distribute across sums. So I'm going to just contract something, make that a single variable so it gets easier. Now if you look at this, what makes this annoying? What makes that hard? Yeah.
The square root of x.
The square root of x. Like if it was just the x, that's super easy.
Yeah.
It's super easy if that was a single letter, right? Let's make it a single letter then. I'm going to do a substitute. I'm not going to do u substitution because we're going to use u in the integration by parts after. You're going to realize that. So I'm going to say let t, I'm going to do a t substitution. Set t equals the radical of x. Okay? So I'm going to want this to look like an e to the t. Okay? What does that mean about dt? What is the derivative of that?
Over 2 root x.
Now at this point you start panicking, well we don't have a 1 over 2 radical x. But that's actually fine because my t is radical x. That's t, right? So notice what I can do here is this is 2 radical x dt equals dx, but that is just t. So 2t dt is equal to dx, right? So now I go here and I swap that out. I'm going to replace the dx and I'm going to replace the radical x. So I am going to have e to the t times my dx is 2t dt, or more concise that I can factor out a 2 and rewrite this in the other order. So this integral becomes that integral. Do we know how to deal with that integral?
Yeah.
How?
Substitution by part. Or integration by
Is that like what you said all the time?
Integration by part.
Integration by parts? What are the parts?
U will be T.
Right, so this here is an A, that here is an E, that's my U. So I can say U equals T, my dV equals E to the T dt, my du would just be dt, my V would be E to the T, and I can plug this in. So this is going to be 2 times U times V minus the integral of V du. So we end up with that. And that integral is super easy. Okay, so that's just E to the T. But what's my T? My T is radical x. That's my integral. Okay. So there were issues in jumping directly into integration by parts. At this point, the only other thing you know about is substitution. So now you say, okay, maybe I have to do a substitution first. What do we substitute? The thing that makes it look easier, right? The radical is obviously the issue, so substitute the radical. Now, whether or not you find the derivative is there, it's almost besides the point, because oftentimes you can rewrite the expression here in terms of the substituted expression anyway, so you can eliminate the need for that. Another way you can think about this is that you can always get the derivative hidden in there, right, by like multiplying and dividing by something. Right, so I can put the derivative anywhere I want it by just multiplying and dividing. That's another way you can think about it, but it's just as nice just solving for dx and writing all the other expressions in the new variable. So we have that. Okay. Any questions? That was a tough one, just to wake you up. Okay, let's try a little bit. B is a little bit nicer because nothing is really hidden. Everyone's out in the open that you're going to need to take advantage of. Okay, so you have something like that. What do you do? Yeah.
Can you have t equal x squared? And then replace the x.
T equals x squared, so your dt would be 2x dx.
And then the x cubed would be 1/8 t cubed. That work? The x cubed.
I'd probably prefer to think of it this way. So think of the x cubed as x squared times x, right?
Mm-hmm.
And then you have the x here, right? And what is the x squared? The x squared is t, right? So I can replace the x squared with t. I'm going to have 1x left over. That comes attached to the dx. So in other words, I would have, let me just write that out. I'm thinking of this as x squared times e to the x squared times x dx. Move one of these x's off the x cubed, attach it to that. Now this part here is 1/2 dt, right, from here. This part here, well, that's just t, and this part here, well, that's just t. So ultimately, this guy reduces to 1/2 the integral of t e to the t dt. Which is the same as this guy, we already know how to deal with that. So that's 1/2 times t e to the t minus e to the t plus c. Except in this case, your t is x squared, so your answer is 1/2 x squared e to the x squared minus e to the x squared plus c. Questions? Feels shaky?
So this doesn't require any integration by parts at all or anything?
Oh, we did. I just didn't show it because we already did it. Integration by parts happened. Like to integrate the t to the t, we did integration by parts. It's just that it's like the third time we're doing this now, so just wrote that on the answer. Let's keep going. What'd you do with this one?
Let x cubed be t. Then dt is 3x squared. And then dt over 3 equals x squared dx. And then just substitute.
Right, so we have 1/3 times the integral of well, e to the t dt. No integration by parts necessary. That one was a trick question. 1/3 e to the x cubed plus c. That's straight up substitution, no integration by parts. We just switching the cubed and the squared can greatly affect the problem. That was just a straight up substitution. What about sine inverse? What do you think?
Can we do the tabular, the new one that we learned?
Sure. You'd have to know what pieces you're going to choose, though. What are the pieces?
Sine inverse is u and x is v. Right?
Well, there is no x, right? It's sine inverse of x. This x is
Oh,
actually
okay.
inside the sine inverse.
Yeah, sine inverse of x is u and then 1 is v.
So you want to think of this as there's a 1 here, dx. Okay? So u is equal to sine inverse of x. Your dv is equal to 1 dx. What is the derivative of sine inverse?
1 over root 1 plus x squared.
1 over the square root of 1 minus x squared. And the integral of this is just x. So remember, in terms of the inverse trig functions, I expect you to know about sine inverse and tan inverse, right? You should know that what the derivative of sine inverse is and what the derivative of tan inverse is. Derivative of tangent inverse is 1 over 1 plus x squared. Okay, so now u times v minus the integral of v du. How do we do with that?
Substitution.
What do you substitute?
1 minus x squared.
So it's u equals 1 minus x squared. Well, let's do a little better. U squared equals 1 minus x squared. Get rid of the radical. 2u du is equal to minus 2x dx. So my u du is equal to minus u du is equal to x dx. So this part here, replace with minus u du. And this part here, I can just replace with u. And so I would end up with x sine inverse of x minus the integral, well it becomes plus now, of u divided by u du. That's just 1 du, right? So that's x sine inverse of x plus u. Let's see. And our u is actually the square root of that guy. That is the integral of sine inverse. Try the other two. See how you feel. If you're like, yeah, I got this, then maybe you got it. If you feel like, I don't know, then find a textbook, look up the integration by parts section, do all the problems in the section. Okay, and then try to finish that by Tuesday, and I'll see you on Tuesday. And your recitation is on Tuesday, right? Okay, so you have a quiz on integration by parts on Tuesday.
Is it going to also have the other one, the table one?
The tabular integration is optional. Tabular integration is just another way to do integration by parts. Right? You don't really think of it as a separate thing, really.
So very part of it.
It's just a nicer way to do it if you're in the situation where you have to do it repeatedly. So enjoy your weekend. Start practicing.
Jhevon,
And yes.
the access code for.
I'll email it to you guys. I think that will be set up by next Tuesday. So.